I've been asked a number of times to go through how to make a kiln that's suitable for the kind of work that we're going to be doing, and it's quite a suitable kiln. I think personally it's quite a good kiln. Now it's not very expensive, but you do need to get some bits for it, because we want this kiln to be properly rated rather than guesswork. And because of the way we're going to make it, there aren't ridiculously long drying times or any pre-firing procedures that you have to follow. You just make your kiln and you can use it. Now, what you see me leaning on here is a bunch of fire bricks. They aren't that expensive, and I bought 6 of them. You're going to need 5, so I bought 6 in case I broke one. I'd suggest you do the same thing. The kiln's going to be about this size on the internal. We're going to fiddle around with this. And your kiln breaks down into 3 bits. There's the kiln body, which is what we're basically going to make this out of. There's your electronics, and then there's the enclosure. Now, for the body, you need these bricks, because these bricks are quite soft in themselves, but hard enough to stand the abuse that we're going to put them to. But they're not themselves enough insulation. You also need some of this stuff, which is ceramic blanket. When we add the ceramic blanket around there, we get a beautifully insulated kiln that's hard enough to put things in and out of, and strong enough to support the heating structure that we're going to put in there. So it gives us quite a nice kiln structure that's relatively quick to make and dry, as I say, and does a really nice job on the insulation, because a kiln works really by balancing the input heat with the input lost. So you can heat the kiln up slowly if you don't put much heat in. As long as it isn't actually losing that heat, it will get up to temperature. If you want it to heat quickly, you have to put more heat in, but still prevent the heat loss. So insulation is one of the prime things about a kiln body. And the insulation is mostly best bought. Now that seems horrible, but to be honest, it's true. I've seen such a lot of things using perlites and vermiculites and water glass, but these ones I've got here are rated to 1260 degrees. This stuff here is 1400 degrees. We're going to glue the whole thing together with this material here, and this is rated at 1200 degrees. So the overall kiln will go up to 1200 degrees centigrade, no worries at all. Your working temperature for the stuff that we do mostly, and 95% of the time, that's the temperature range I'm in, is 800 to 1200 degrees. That's where most of this work takes place. If you want to get a higher temperature, you're going to need to get higher rated stuff. These ones are the mid-range, and so they're 1260, but you can get these 1400 degrees C. If you want to go up to about 1600 to 1800 degrees, you need a different refractory. The problem with a lot of the homemade stuff is that at those temperatures, water glass melts and just forms a pool. Perlite will spall, it will splinter off. Vermiculite, forget about it. So when you want to do those kind of temperatures consistently, you need a consistent material to do it. And this stuff you're not going to be able to replicate yourself consistently. They're not that expensive. Just buy yourself a bunch. They cut really easily, so it's great to work with them. And if you make a mistake, you're going to waste about £5 instead of hours and hours and hours of work. So this is the best stuff to get, I would say. Now when it comes to putting the electronics together, we'll go through this again later in this section. You need some of this stuff, which is resistive heating wire. It's available on the net. It's extraordinarily cheap. This is the one that you wire your kiln coils out of. When you want a new coil, you wind this stuff up. You just need to work out the maths for it, and it's really simple stuff, and we'll go through it to get an idea of how much length of that stuff you need, and that again is dirt cheap. And we need some control. The main control are these things. This is a PID controller along with the thermocouple. You usually buy this as a kit. And here's a solid state relay. These 3 components come together. They're usually about 20 to 30 pounds, something like that. And that'll give you control up to 1300. So well within the range of what we're constructing. If we're going to construct something that can last at 1200, our control will do 1300. Normally you rate these things all together. So all of your materials, your wires and your controls are heat rated for those heats. You want more than that? You have to buy the right equipment for more than that. It's easy to tell what the right equipment is because it says on the advert when you buy it, rated to such a temperature. Don't buy it if it won't go into the temperature you want it to go into. Like I say, we're aiming for 8 to 1200. This kiln will cope with that easily. Okay, so I mentioned it was 3 parts. First part we're going to construct is the body of the kiln, and we're going to make it from this, and this. Those are the 3 components we're going to make our body from. It'll be roughly this size. Now what we want to do is to take these bricks, because they're too chunky as they are for what we want. We want a lab kiln, and we're going to cut those bricks in half down there. So all we have to do is draw a line on there, saw them in half. The beauty of this stuff is it cuts with ordinary saws, ordinary equipment. It's not terrible, it's not difficult, it's a piece of cake to cut that with a panel saw. So that's what we're going to do, we're going to cut those in half. Okay, so we've cut 4 of those in length halfways, and these will actually be your kiln body. You will have a bit of variety because you're hand cutting them, so choose 2 that are relatively level and they'll be the floor. Choose 2 more, and then we need to mark them up with a 15mm diameter mark in a U shape, just like that. And they're going to be the sides. We have 2 more for the top. And then the other 2 go at the back. And that's your kiln body. Now obviously these are a bit high, so we need to mark them off and saw them off. So they're going to get sawn off there. And these 2 are going to get carved out for the coil, because that's where the coil goes. Now to carve them out, what I use is this. It's a bit of 15mm copper pipe. It's got a slight angle cut, and that's actually great as a gouge for just gouging out that line. Now the secret here is patience. Don't go at it like crazy. It will just gouge really nicely. So you just be gentle with it. And keep gouging there, and you will get that out. And you need it to more or less the depth of this pipe. If you're a bit impatient, another thing you can do is use this. This is called a pad saw. And if you cut those lines out with the pad saw, again, going at it gently, you'll be able to gouge it out that much more easily. So I'm going to gouge those out. Okay, so once we've cut our U-channels out in both our end bricks, you need to match them up, draw a line and drill a hole, because that's where the wires are going to go through. When that's done, all we need to do is glue it together with our high temperature silicate putty. Then we glue on the sides and the back. Okay, that's it glued together. Now, it has no structural strength worth speaking of, so what we're going to do is put these angles on the 4 corners and use these hose clips fastened together around it, tighten them up to band those together, and that's going to be plenty strong enough. Okay, believe it or not, that's actually the basics of the kiln done. So it's all nice and firm and fitted out. Obviously we've got to put the coil in, we've got to put the control electronics in, and they're going to be the same. This will work just fine actually, but we need to get it up a little bit higher than 800, and we need to do that easily. So what we're going to do is use that ceramic blanket and put another wrap of insulation on it. So that's what we're going to do. But there's a divergence here. Remember I said earlier it splits into a number of parts: the body, the case, the electrics, the door. Now we've done the body, the main body of the kiln, and that's pretty much the same whatever you're going to build. But the case is a different matter. Now you could do without a case altogether, bolt some legs on, have it standing up there, and then you're going to have yourself a kiln, and it's going to get to about 800 just fine. I want to get higher, and I tend to use things that I find, as you know. I like to repurpose stuff. You don't need to, you buy yourself some sheet metal and bend up a case, no worries at all. Me, I like to repurpose things. I found this. It's a stainless steel bathroom cabinet. The mirror was broken, so somebody was throwing it away. So I took off the mirror because it's going to make an awesome stand for this. So I'll be able to put my display and my on-off switch right there in the front. This is going to go about like that, something like that. So I'll put the door into here, so the door opens from this bit here, put more insulation, and then bend a case like that, which I'll slot over the top. My control electronics, which is really just the solid state relay and the connections to the mains, are going to go back here where nobody's actually going to get to them. But I just thought that was kind of cool actually. So I like that a lot. So I'm going to modify this so that my kiln body fits my case. And if you do a different thing, you're going to have to do that as well. The kiln body, like I say, is always the same. But there's always going to be a modification to get it to fit whatever thing you have if you're using found objects. And that's what I'm doing. So I'm going to have to put some brackets on here because I need to raise it up by about that much because I need that much insulation in it. Brackets on here, load of insulation, exterior case, connect the electronics, make the door. That's what I've got to do. If you are using a different thing, then obviously you've got different jobs to do, but it's essentially the same thing. It's really just what makes it look pretty to you. I like that, so that's what I'm going with. Now the information you need is really useful because it doesn't only help you build a kiln, it'll help you recondition kilns as well. Now as long as the fire brick in the kiln is in good condition and the case of the kiln is in reasonable condition, you don't need to worry about the electrics contained within the kiln. All of those can be replaced and replaced cheaply. I'm going to take you next door. It's a bit echoey, so please forgive me on that. And then we'll come back in here. But I want to show you the kiln that I bought. Okay, please forgive the sound quality. It does echo in here. This is my kiln. Now I paid 150 quid for this and I bought it because the bricks in there are rated to 1600 degrees and they were in perfect condition. Everything else was shot to hell. So I had to replace all of these coils. Now if you're going to use a kiln for a while, you're going to be replacing the coils. So learning how to make coils is a really valuable thing to have to maintain your kiln. Once you've made the kiln, you're going to have to maintain it at some stage. Unless you want to pay a maintenance fee, you're going to need to know how to make coils. So making and fitting the coils is a key thing in building, reconditioning, repairing or maintaining your kiln. Again, sorry for the poor quality of both the sound and the image here, but this kiln's a bit heavy. Here is a view of the back of the kiln. The coils all come out and then join up with the solid state relays there. Those solid state relays are controlled by the PID controller. That is essentially all of the electronics your kiln contains. Incidentally, the reason I'm doing it this way is because I'm working on the assumption that you don't have a welder. If you have a welder and can weld, awesome, weld everything. But not everybody has, and this can be made with hand tools, and that's what I like about it. Now the reason we're concentrating on coils and the electrics here is because, like I say, it opens up so many more doors to you. The easiest, quickest, cheapest route, believe it or not, to kiln ownership is to buy an old one. You find an old one, bricks are in good condition, case is in good condition, and you know your electrics, that's going to be the cheapest way of getting kiln ownership for a decent kiln. I enjoy building things, and I know lots of people enjoy building things, and there's a sense of pride in that, so we're building it. But like I say, we're splitting it into parts so that we can review the certain sections, and this one really is going to be about the electrics, obviously. We'll do a third part where I finish this, but to be honest, the third part is all cosmetic stuff. It's just stuff I think is interesting to look at and to finish the kiln. And the other thing we've done is put these uprights here, because that's where the door's going to hang. So when we're thinking about the electrics, the essential bit you're going to buy is this. It's the resistance wire. Now this comes in a whole range of gauges, and it always says on it what the resistance is. This particular one is 1.2 millimeters and it's 1.72 ohms per meter. I choose that because I find it the most convenient. It just makes coils that are very adaptable to medium to large kilns, and I tend to use this material quite a lot because I find it a good grade of wire to be using. Now, all wire gets hot, obviously. It's a heating element. And because it's hot, it spalls, it flakes, it's stressed. They do eventually break. So just to reiterate, knowing about your coils really is an essential thing, I think. Now we're going to plug this into a main supply, and there are two main supplies we've got really. That's 230 volts, one 10 volts, and it's going to have an effect. Now a main supply is an AC circuit, and what you usually measure with AC is something called the impedance. The impedance is the resistance plus the reactance. Now, impedance only has an effect if the circuit has reactance. And the only things that have reactance are capacitors and inductors. So if you've got a capacitor or an inductor in your circuit, then you need to pay attention to the impedance. Here, we're using coils, which are pure resistance. There is no reactance in a coil, in a heating coil. It's just a big old resistor, that's all it is. So we can ignore the reactance, and we can just use Ohm's law. That makes everything super, super easy for us because it's volts equals current times resistance. So we want to work everything out. That's what we use. And it's V equals IR. V is volts, I is current, R is resistance. Because we need to know how big to make those coils. Now, if we're going to plug this thing in, and we plug it in into a UK supply at 230 volts, and we've got a 13 amp fuse on the end of the plug, there are limits. We know we're only going to be able to draw 13 amps. We know it's going to be at 230 volts. So we'll know from V equals IR what the resistance has to be. If you calculate that, you'll find it's somewhere around about 18 ohms or so. With this, we know this is 1.72 ohms a metre. So if we divide 18 with 1.72, it gives us a number of metres of this we need. So if we cut off 10.5 metres or so of this stuff, it will have a resistance of 18 ohms. If we plug it into a 230 volt supply, it will draw 13 amps. It's that simple. As long as we keep that relationship, we know what it is that it's going to be. Now, if we want to know the watts, which is volts times amps, it's going to be about 3 kilowatts, something like that. That's quite a lot for this. It's 3 kilowatts, about the same as your kettle or a normal heater. So you've got tons of safety of margin. We're going to put lots of insulation. We're not really too worried about the ramp up time. It doesn't need to be massively quick. So we can bang on a few feet of resistance as a safety margin against the fuse blowing. So if I cut off 12 feet of that, 12 meters of this stuff, I'm going to have plenty of resistance to keep my amp draw below 13 amps, in which case the plug that I use is not going to blow its fuse, it's just going to be Jim Dandy and happy. Now I don't obviously necessarily need to plug this in via a normal socket. I could wire it in through a cooker socket or through a shower socket and use the appropriate gauge wire. That's a lot of trouble to go to. Really, I just want to put a plug on it. But I could do that, in which case I can go up to 36, 40 amps, whatever it is. And on 2.5 mil, I could do 32 amps if I wired it straight into the board. Don't plan on doing that, but I could do, in which case that amp draw would change the resistance that I need to put in there. Now, because a lot of countries have a 110 volt, clearly that's going to have an effect because it's V equals IR. If you've got a 110 volt supply and a 13 amp limit on it, then you're going to need about 13 ohms instead of 18 ohms, and it'll go down to round about 1.5 kilowatts, which is going to be ample, really. So it's really easy to make this stuff using V equal IR and V times A to get your kilowatt draw on it. It's dead simple. In order to get that resistance, all we have to do is cut the right length of this wire off. That's all we have to do. And we can wind that up. Now, we've got two sides to this. So there's a coil on that side and a coil on that side. And we're going to bring out the back and we're going to connect them. There are two ways of connecting it. We connect end to end, in which case they're series. So we have an end, our coil, an end, connected to the other end, our coil, and then going out. That's an in-series connection. And if we do that, and we connect our supply to the two ends of those coils, then that resistance in series adds up. Now we're quite lucky because this is really quite a small device, so we can just add them up in series. So if we get two 6 meter lengths and add them, it's equivalent to one 12 meter length, which is exactly the resistance that we want. Now you do have an option, obviously. You could connect the two coils in parallel, so you have two wires, one live, one neutral, and they go to two separate coils. That's in parallel. What happens when you connect resistors in parallel is the resistance always goes down. Resistors in series, you just add the resistances. Resistances in parallel, you add the reciprocal, that is 1 over the resistance, and then take the reciprocal of that to give you what your resistors in parallel actually are. Dead simple, just scan on Google, find out what the formula is, plug it in, and you'll get your resistors in parallel. Resistance in parallel, obviously, you need to make sure that your total resistance of your coils as they're connected still follow the V equals IR rule to make sure that you don't draw the more amps than your supply can supply you. Because if I do resistances in parallel of 2 at 9 ohms, the overall resistance will be 4.5 ohms, half. So instead of drawing 13 amps, it will attempt to draw 26 amps twice. And that will blow your fuse. So it's easy to do it in series, just add them together. On a device like this, there's no real challenge. On bigger kilns, you do a resistance in series and parallel, but then you're much more likely to have wired a bigger kiln into its own socket. My kiln, for instance, there is on 6mm cable. It's a resistance in series and parallel combination, but it's a 12 kilowatt cable kiln, as it needs to be, being such a big kiln. This one, tiny kiln. So that's a lot of information about how to calculate these coils. But it really just comes down to knowing what your resistance needs to be to limit your amp draw given your voltage supply. That's all there is to it. Once you know that, then you just cut yourself off a length and wind it in a coil. Now, coil winding I actually really enjoy, and it is a piece of cake. Okay, so this is how I wind coils. I use this little mini lathe to do it. Now, you don't need a lathe to do it. You can do this by hand, or you can do it with a drill where the drill's fixed down. It's a little bit more tedious, but it's the same principle. What I've got in the lathe is a bar, and it's 1.2 millimeters. Remember, we cut that channel at 1.5, so you choose your bar to make your end coil to fit the channel that you just cut, and it's basically just a little bit bigger. So I've got 1.2 here. I'll wind this quite tightly. When it's wound, we undo it and it springs out a little bit, and it will fit beautifully into 1.5 mil. All you do is put a bit of tension on the wire and then turn it on. And it takes no time at all to make a beautiful tight coil. So I'm going to finish this coil. Again, there's the coil finished. It's surprising, isn't it, how 6 meters shrinks down to so little. So with that is actually the finished coil. Now it is touching, and we need to stretch it out. But that's the finished coil. Incidentally, I always leave my chuck key in here, and I get told off by it quite a lot. The reason I leave it in here is there's in fact a safety switch, where you can't turn it on if the chuck key is in. That chuck key's got to be removed to turn this machine on. So you shouldn't leave your chuck key in the chuck. General as a general rule, perfectly true. But at this specific instance, it's got a safety switch in it preventing it starting if that's in. It's the safest place for it. Okay, so there's our coil. Now, I've measured the size of that channel that we cut, and it turns out it's 45 centimeters. So I need to stretch this coil out to 45 centimeters. But you'll see what I'm doing as I talk. I also need a bit that's going to go through those holes that we drilled, if you remember those holes, because I need the coil to get into the back so I can connect it. So I unwind about that much. Again, we've put plenty of leeway into this, incidentally. We don't need to be too worried about all of this stuff because we've got 12 meters when we needed 10.5. So plenty of leeway that we're not going to stress it out in terms of its draw. So we just unwind a bit of that. It's going to be more than enough. And I've positioned this so this bit and this bit are 45 centimeters apart. So if I put that there and stretch that, I'm stretching the coil. Now obviously it'll spring back because it's a spring. So what we need to do is stretch it beyond that, and you'll feel it as it stretches giving. You can just feel it relaxing. It will spring back and you'll go back to the relaxation stage and you can see where you are. And you need to stretch it out so that when it springs back, it finishes where your mark is, because that now is a really nice finished coil. Then all we have to do is feed it in the channel. So I'll give you a close-up of feeding it in the channel. Okay, so there's the channel we're going to feed it into, and if you remember earlier, we've drilled those holes in. You put one wire into the hole, pull it out, lay your other wire in, hook your other wire into the other hole. And then we put the coil into the channel that we just made. And there we go, fits rather nicely. Okay, we're at the back of the kiln now where we poked the coils through, and you'll see these are joined by that brass connector. So that's the top of the two coils joined by that connector, which I get from this stuff. I just chop them out. Now they've been in that big kiln for about 2 years now, something like that. No problem at all. So they form a nice junction that'll connect the coils, and you'll see that the end of the coils I've terminated with the same brass connector, because that's where my supply wires come in. My neutral from the supply goes straight into one end, and then the other end goes into this thing, which is a solid state relay. And the solid state relay is in fact just a switch. So the live supply goes in one side, and then the live supply comes out of the other side and into the other coil. Remember, the neutral goes in this side. And it doesn't matter which way around, 1 or 2. This is rated for 24 volts to 380 volts of VAC. 40 amps, gonna do just Jim Dandy. You saw these actually in the bigger kiln where each of my coil sets is controlled by one of them. Now on this side is where the PID controller comes, and that sends the on-off signal, so that's only 3 to 32 volts. So anywhere between 3 and 32 volts, we can actually just switch that on and off, and when we do that, it's just like operating a light switch. It switches the live. Now it matters which way around this goes. 3 is plus, 4 is minus, and that's a DC input. This takes the AC and switches it. That's all it does. And that's the control electronics at the back of the kiln. Now we'll connect that up when we do the rest of the connections, but that's the connections for it. And it really is, if you like, as complicated as that. That's how easy wiring kilns gets. Okay, I get a sense it's getting to be a really long video with a bit much information in it, so I'm going to leave it there on this one. So, to recap, what we've done is learn how to make our coils and how to connect them in the back together. We still have to put the control electronics in to control those coils, but we'll do that in the next video. We still have to finish the case, and we'll do that as well. I'm not quite sure which way around it will be, but I think that the coil making stuff is really, really important because it opens up so many possibilities, particularly grabbing and refurbishing an old kiln. And you are going to need it when it comes to running a kiln anyway, because these things do. Okay, so this is all about the cosmetics of it. It's making the door, the final wiring up, and then the cosmetics of the build. Because the outer case is going to change, really, depending on what you can find, what it is you want to use, what tools you've got available to you, a whole host of things. Now, I've tried to make this with the minimum tool set required, so I've used hardly any tools to actually make it. It shouldn't be a stop to you if you don't have a CNC lathe machine or anything. That shouldn't stop you trying to do stuff, because you can do the most amazing things with just the barest minimum of tools, a bit of creativity and good use of what you find around you. I sound like a wumble. Anyway, all we've done with this is from that original one, if you cast back on the previous video, we made the frame and put the bricks in. All I've done is I've put a base on it and then a face on there. Now I was going to make this out of a bit of stainless steel, but I came across a load of these. These are perforated shelves from a server unit, I think. And they're a nice good bit of grey chunky steel with lovely perforations in, and I couldn't resist. So I changed the design, and that's what you can do when you're doing this stuff. So I cut out this centre section here so I could get in there. They used one whole piece here as the stand for it to be on, and personally I think it looks really cute, which is why I did it. I like the look of it. Now the next thing that I did was make the door. And to be honest, it's a piece of cake. There's the door. You can see what it is. It's really just 2 bits of angle iron here and here, 2 bits there held together with bolts. and then I stuffed the bricks into it, and of course I sealed the bricks with that silica sealant that we used on everything else, and cut out a plug so that that plug here will fit into that opening. There's about a 2 centimetre depth to it, so when it closes, it'll close in there. And I made these bits a bit longer because I put some 10mm threaded bar here, a couple of cap nuts on it and a bit of plastic. That's my handle. And I did the same thing here, but I made the bar longer, and this is copper pipe, and that's my hinge. There's a bit of angle here with the bolt in it because this fits by dropping in a 10mm hole I've drilled in the base, just like that. That angle goes into there, and that makes the hinge of our door. So now if we put a bolt on there, there we go. We have really quite a nice door that works really well. Now, I'm not too bothered, I'll tighten that up again in a minute, I'm not too bothered about things like latches and, for a kiln this size, a cut-off switch. I just think it's completely unnecessary. None of the other kilns I've ever bought or owned or have at this moment, at this size, have an emergency cut-off switch. They're usually here on the door. They're a little angle that press a normally open switch. So unless the door is closed, it won't turn on. Now you can add that if you want. You just put an angle onto your door there, put your little contact switch there. When the door closes, pushes that switch and then it'll turn on. I'm not going to bother. If you're that worried about it, put a safety switch on there. The other thing you could do is put a clasp on there, and that's really easy. Just get yourself a bolt, stick a nut on it, and then swivel it round and tighten it down. It'll keep the door shut. Again, I'm not too bothered by that because it's got enough weight and mass to keep that door shut all by itself. So that's the door finished and attached. As part of the facing finished and attached, all we've got to do is wrap this in the ceramic fibre blanket, finish the wiring, and then it's actually ready to go. So that's what we're going to do next, is we're going to do that wrap. Now, a word about this ceramic fibre blanket. It isn't nice stuff. And if you're working with it all day long, every day, you really need to take precautions with it. If you're doing a job like this, where you're going to use it once, then you need to be sensible with it for sure, but you don't need to worry that you're going to die of silicosis tomorrow. Do sensible stuff like pull down your sleeves. You pull down your sleeves so the fibres can't get into your skin. Now, I have refitted roofs with glass fibre and got glass fibre into my arms, and it does itch for a few days like crazy. So it just makes sense, pull down your sleeves, put some gloves on and wear a mask, and you're just going to be Jim Dandy. You do not need to worry about dropping dead from hideous lung diseases. If you're working with it all day long every day, sure, you need some real good gear to take care of you. When you're doing something like this, just be sensible and you're going to be okay. So we need to wrap this with the fibre blanket and then fasten that down with some stainless steel wire. So we wrap it, put a loop of wire around, twist it, and then make the coverings. And that's what we're going to do next. Okay, so all we've done is give it a couple of layers of blanket. It's 1 inch blanket, so there's an extra 2 inches of insulation there. We've taken some of this, which is just stainless steel wire, feed it through, pull it tight, give it a couple of twists, and there's 3 of those. Now I have seen this with aluminium foil on top of that, but I don't know whether it does anything or not, so I decided to leave the aluminium foil out. If you want to put the aluminium foil in, well, knock yourself out. Now once we get the cap on this, you're not going to disturb it, so really stop worrying about it if you are. If you go sticking your nose in and breathing it deeply while poking it with a pencil, you probably shouldn't. But once we get the caps on, it's really nothing to worry about. But there's the extra insulation. Obviously, we've done it all the way around. The back's still open. I just tightened up that door so that it does a really nice job. And now all we need to do is make the covers out of this, and I'm going to cut them from this stuff and then finish the wiring up, and we're ready to go. Okay, and that is the construction finished, and it's quite pretty, even if I say so myself. I like this. I like the sort of look of it. So all we've really got to do now is wire it in. So we've done the coils, we've done the basic structure, we've finished this off, and remember, this is going to look different to the one you make, because I was just lucky to find these shelving pieces that I used for this. But all the basics is there, and the only thing we need to do now is actually wire it up and fire it up and get something going with it.
Okay, so here's the back of it. Now, I don't like things crowded in there, so there's going to be nothing in here. There'll be a plate over the top, and the only thing that I need to put in now is this thing, which is the thermocouple. So that measures the temperature, and I've drilled a hole as near to the middle as I can get it and right at the top of the kiln, and the thermocouple just slides in there. I've made a little bracket so that we can bolt that thermocouple down and screw it onto this piece of steel so it's nice and fixed. And here we've got a rubber inlet so that the wire will come in here and the thermocouple will go out of here. We'll strap everything down and we're going to wire that up just as we talked about on the wiring video. Okay, that's it wired, nice and uncomplicated, exactly how it should be, because this is the bit that's going to need maintenance, and one thing you don't want is to cram stuff in there so you can't get to it. So basically leave lots of room. It makes everything really that much easier, that much safer, and you are going to be repairing this at some time, so it's a good idea to do it. And you can see I've wired it up to a neutral to one end of the coil, and that neutral goes to the neutral supply. It goes up and down the coil, comes out here, is joined to this coil in series, comes down here, and then goes to that live. That live does not go to the supply, that goes to the switch. So that's actually a switched live, and we switch that using the solid state relay. And you'll notice I've earthed the case as well, because it's a big metal case. And we've got some open wires in there, so I've got an earth on there, and the thermocouple is just tidied away with little stainless steel wire ties to keep everything from sagging or dropping or touching, and then it comes out of this sealed exit. And this sealed exit is IP65, I think, and so you can give that a good tug and nothing's actually moving, so it's nice and firm. These wires will go to the actual control box where all the controls are, but that is how you wire the back of the kiln up.
Okay, the wiring really is simple. Now we've got everything in here, we don't have to worry about it particularly and try and cram things in there. Now if it's a big kiln, like in my big kiln there's lots of space, then sure, I'll put the stuff in the back there. But a little thing like this, we start cramming things in, then there's a chance they'll touch, they're a pain in the neck to repair when you actually have to repair them. So I like to keep everything away, nice and neat and tidy, plenty of room and away from things. That's just my choice. You find people bolting on boxes onto the side, you find them doing all sorts of stuff. And me, I like it out of the way so that I can get to it when the inevitable happens. But it's really pretty simple stuff because you're just dealing with two bits of equipment. This one has a picture on telling you what to do, and I'll give you a close-up of that in a second, and this one has a picture on it telling you what to do. So let's have a close-up of that.
Okay, so you only really need essentially two bits. You can put a switch in there if you want, or you can just rely on the switch on the socket. I quite often put a switch in, and I usually put a double pole switch that switches the live and the neutral. And now, it's dead easy. There are just two sides to it. The neutral comes in to one side, and it goes out of the other side. And then when you turn that switch, the neutral will be switched. Same thing with the live, but it's on the opposite side. Now if we have a look at this PID controller, then there are a number of little terminals on the back there, and then on the side there is invariably a picture. If there isn't, it'll have come with the sheet. If it hasn't come with the sheet, you just look it up, and the information is abundant. There's lots of it, really. Now here we've got 1 and 2, which tell you that it is the AC in. So it doesn't matter which way around you do this, but I usually put the live into 1 and the neutral into 2. Now it does need a supply, so it's not a switch. So live and neutral into 1 and 2. You can set alarms, and the alarm function are here on 6 and 7. I never do, to be honest. You can attach different kinds of relays where you have different timing sequences. Again, I never bother, so 3 never gets used. 4 and 5 are the ones that you use, and there's a little symbol telling you that 4 is plus and 5 is minus. Then if we come to this side here, we've got 8, 9 and 10. 8, 9 and 10 are in fact where the thermocouple goes. It's the sensor. Now you don't connect 8, which is an alarm. It's 9 and 10 that you connect, and again it tells you which one is plus and which one is minus. There's a little plus sign by 10, a little minus sign by 8. And if you have a look at the end of a thermocouple, and there's one there, it's got blue and red to help you. So that's the plus, that's the minus. So there you go. check that's the right way around, in there. And you just screw those down and you're done. That's it for the thermocouple. Here is where your comes from the switch into here. So from the double pole switch live goes in there, double pole switch neutral goes in there, and you're done. It's as simple as that. It really is. From here we run 2 wires to this. This is the actual relay. Again, it's just another switch. And it tells you that 3 and 4 are plus and minus. So we connect where it says SSR minus to minus and SSR plus to plus. And that's all you do with that. Now on this one, this is where the live gets switched. So this is live in and live out, and it doesn't matter which way around it goes. So from the double pole switch, you pull another live that comes in here. Then this one goes straight down this white wire that we connected up, and that live is the one that goes to the live coil. So remember, we've got a live, a neutral and an earth. The earth just gets connected to the earth in. The neutral gets connected to the neutral double pole switch on the switch side. This live goes in here, and then the other live goes in there. And that is all there is to it. So this is what it looks like when it's all connected up. There's the double pole switch, there's the relay, there's the PID controller, and there's the thermocouple. Once you get that all connected, it looks just like that. It's a jumble of wires when you get it together, but if you think clearly about what it is you're doing, it's a piece of cake to do that. Okay, that's everything wired together. The whole thing's finished and it's now ready to go. Okay, so I was thinking about this a bit, and I thought that maybe I had skipped through quite quickly one of the more, if you like, complex bits of this job, and that is wiring the control box. In the main video I said just do this, this and this. So what I thought I would do is actual step-by-step of wiring it so that you could follow that if you wanted to. Now if that's not the video for you, then obviously just don't watch the video. But it is some information I would have appreciated when I first started doing this, because it can be a bit confusing and it's a bit difficult to work out how it goes, so I thought it would be helpful just to do the wire up. Now what you can see here with the 2 bits that I've been talking about, so there's the solid state relay, there's the PID controller, and I just fabricated this aluminium box by folding up some sheet aluminium, and in there I've got a double pole switch already waiting. I pulled that from a PC supply. So the double pole switch originally at this end connected to the mains, and that's the one we're going to connect to the mains. If we follow that through, we'll see that it goes to that side of the switch, which is marked 0, and that's always the way it is actually. That's good practice. The 0 is the side that your live supply goes from. On the 1, that's when you've switched it on, and that's where your supply comes out of. So that's the main control switch right there, and these ones that come out of the 1 side are the ones that we're going to be using to wire everything together with. Here we've got a couple of IP65 rated plugs. They screw into the back, they're nice and firm, there's a rubber bungos in there. This screws down on it and gets everything really good and secure. There's 2 of them because one of them goes to the kiln and the other one goes to the actual wall socket that we're going to put a plug on. And of course I've grabbed a length of flex, it's a rubberized heat flex incidentally, and stripped the ends ready to go in there. So we've got a length of flex appropriate. The other thing that we've got obviously is coming from our kiln is the white wire that goes to the heating elements and the earth, and the thermocouple wire, which is this silvery wire. And those are the ones that come from the kiln. They actually just feed in either one of these. I tend to choose the lower one, not for any reason particularly. Feed in the screw. Then the rubber protector. This is the bit that forms the seal. And then you can pop those in. Okay, the first thing that we're going to wire up is the PID controller, and it's much easier to wire it outside. It has this locking ring on it, and that locking ring slides onto there with these clips engaging in that little ratchet. So you need to feed on the locking ring on the inside of the box, and then these wires go through the window that I've cut in the box that will actually go to that controller. So we wire these in and shove it all in, it's all in place. This one is the thermocouple, and we'll deal with that first because it's really quite easy. On the little picture, and remember they always come with this picture or a data sheet, you'll see 9 and 10. So all of these little numbers here correspond to the numbers that you'll see printed down those terminals. So we see 9 and 10, and it says TC on it, which stands for thermocouple. 9 is minus and 10 is plus. And if we look on this side, you have to work it out. There we go. 9 and 10. So that's number 9 and that's number 10. So it'll be those two terminals that we're using. 9 is the negative. And on thermocouples, the negative is always blue. We slide in the pin, screw it down, put in our positive, and that's the thermocouple connected, so it's all done rather nicely. Now the next thing to deal with is the solid state relay. And there's a solid state relay there, and if we look at that, it's 4 and 5. Again, check the numbers. That's 4, that's 5. So it's opposite 9 and 10, so we've got 4 and 5. So 4 is the SSR positive. So there's my solid state relay. Now that's going to mount in there. So what I want is a piece of wire, obviously, to go from this through the window, through the lock, and into the solid state relay. So I'm going to use traditional colours, and we've got a brown here. Could use red, I guess. Could use red and black or brown and blue. Just trim that off. And that will go into 4. Make a little loop and bend it around it so that it locks it into place. In a different coloured wire, I'm using blue, and do exactly the same thing. And it never hurts to check you've got it the right way around. So 4 is positive, 5 is negative. Then they feed through the window, then the locking ring, and then we're going to put them into the rectifier. The rectifier will sit about here, so we need those wires to be about that long. So they're a little long, but we can just snip them off. And we're going to do exactly the same thing, but in this time we just have to think about the blue and the brown. The brown obviously goes in the positive, which is number 3, and the blue goes in the negative, which is number 4. Now this is our control signal that comes from the PID controller, so there's never going to be much in the way of anything going down there. That's about 3 or 4 volts, something like that. And exactly the same routine. And that wire's in that side of the solid state relay. So we've done our thermocouple, we've done our solid state relay. The only other thing this needs is the supply, and we see it here at 1 and 2, which are those two there. Now remember, the supply, it doesn't matter which one is live and which one is neutral, so we can put whichever one we want. I usually put live in 1 and neutral in 2, but it really doesn't matter. The 1 and 2 need a supply because this is a piece of equipment. Now we take our wire that came from the 1 on the other side of the double pole switch, separate them out a little bit, feed them through the locking ring, and then back out the other side through the window, and they're going to go into here. Now 1 and 2 will go there, but we need to take a live and a neutral, because this, live and neutral. This neutral needs to go to the neutral on this. This live needs to go, neutral on this and neutral on the supply, incidentally. This live needs to go to the silicon rectifier, so relay. So what we need to do is put them into here. Now the easiest way to do that, or at least a nice way of doing that, perhaps not the easiest, is to strip a bit of the wire in the centre. So a little bit of a fiddle on. And we end up with a bit of exposed wire like that. Twist it round, undo number 1, and we're going to make that our loop, so we can loop around there. Then we don't have to make a joint, and then we also have a nice continuity. That then goes back into number 1. So that will become the live for everything else, and this now has its own live. And we do exactly the same thing with the neutral wire. And that is the PID controller wired. Obviously these go back through the window and back through the locking ring. Push it into place and slide up the locking ring. And that's the actual controller now finished. So we have our rectifier that will connect to the actual live. We have our relay, I keep calling that a rectifier for some reason, and then our live and neutral that have been switched coming out there. Now this live goes into 1 or 2, and it doesn't matter which one it is, so we can put that in now. I'm going to put it into 1. As remember, this relay is in fact another switch. It just switches the live, so we have to run the live through that, so that the control signal that's coming in here will actually act as a switch to switch that live off and on, which is what goes to the coils. So we only have one more connection to make to this, and that's the connection to the coils, which is here. So this white wire that we had goes straight to the kiln, remember? And in the white wire we have a neutral, a live and an earth. The earth will earth on the body of here and earth on the supply which is this socket here that we'll look at again in a second. So the earth will go there. The neutral just connects straight to that neutral, and this live goes to number 2 on the relay. Okay, we can now fasten that down. And I've created a couple of drill holes here where I can put a couple of bolts through to fasten the relay down. All the wires we've got left are the neutral and the earth that go to the kiln, that's this white wire. Then we've got the supply in that came from our switch, and then we've got that neutral that we made. Now what happens is that these two neutrals get connected to each other. Now we could use a whole way of connecting these, including terminal blocks. I quite like crimps because according to the wiring regulations, crimps count as a permanent connection and terminal blocks do not. So I quite like crimping these things. So that's the neutral wire taken care of. Fold it out of the way. And now our earth wire. Now I've drilled a hole in the case right there, so I can put a screw in, a bolt actually. And that's where my earth connection will go. Now there is another earth connection to make, and that's to the earth supply. So that earth's the kiln and earth's the control box. Now we need to tidy this up, so just run the thermocouple wire along the white wire to make sure that they're both the same length. And the thermocouple wire will have extra length, so just pull it into the control box. And then we can close this up here. So slide in the plug. And then the nut. And we can tidy up our wire a bit. Okay, the only thing we've got left to do is to connect the actual supply, which is here. Remember, this goes into the switch. So to do that, we're going to use this piece of flex. It's heat rated flex, got a nice moulded plug and fuse, and there is the in part of it. And we put that in the top one there. On with the nut, on with the seal. Into that, and we can connect the earth up. And all we have to do now is connect these, which we can do by crimping. Okay, that's them crimped together, and we can just tuck them out of the way. And then we can put a lid on that and close this back here just by screwing this connection together to make it all nice and firm. Okay, so when we've crimped those two bits together, then we're all done really. We can tuck it out of the way, tighten up this flex, because this is the one that's going to get plugged in, remember, and that's the control box all wired up, ready to put a lid on it. Now, I know this is perhaps not the most interesting of videos to lots of people, but I would have really appreciated knowing that when I first started doing these things, so I figured I would share that information with you. If you still have some worries, like how do you know which one is plus and minus,
then it is really, it's printed on the thing. So when you get your piece of equipment, your relay or your PID, it's printed there telling you which one's plus and which one's minus. So you don't have to work it out, it says on it exactly which one it is. So you just have to look at it, and very often with these things, doing them clears up an awful lot of mystery as well. I did think about doing the circuit diagram, but I think that circuit diagrams sometimes aren't as helpful as just seeing the physical piece of equipment and how you screw that wire in and where you screw that wire in. So if you take the lid off these and look at them, it looks like a jumble of wires. If you follow that process step by step, then you're going to be able to wire these things up a piece of cake. Anyway, I know it's a bit long, but I really wanted to share that with you because I'm hoping it's useful. So I hope it is useful, and thank you very much for watching.